This is going to be a little crash course on how to represent motion. We've talked about motion, displacement, distance. We've talked about vectors. You should have an awareness and understanding of velocity and acceleration. And now we're going to learn how to kind of model all that, make models using different graphical representations and then ultimately some mathematical representations and models as well. The first type of model I want to show you is known by several different names. Sometimes it's called a motion map, a ticker tape diagram, or a vector diagram. Really, in my eyes, they're all the same. So let me show you real quick a little bit about how these work. Let's say that we have an object that begins at the origin. So you can see that I have my reference frame lined out. It's one-dimensional. I've defined an origin, and my object is starting at the origin. And I can represent the motion of this object. If this object starts moving, I can track it. And the rules for tracking it, for representing motion on these types of diagrams, are that every 1 second you place a dot to represent where the object is located in space, its position. And so I think you can see why this would be a useful tool. Let's say that this object is moving with a velocity of positive 1 meters per second. So in 1 second, it is moving 1 meters per second. For every 1 second, it's changing its position positively. That means to the right, 1 meter. So my next dot would go right here at 1 meter. My third dot here at 2 meters. My next dot here at 3, 4, 5. And there's an object whose motion is a positive velocity moving to the right with a velocity of 1 meter per second. Let's look now at a different object that may be moving with a velocity of 2 meters per second. Let's see what that would look like. Again, it's going to start at the origin. And this time, every 1 second, remember, each second I place a dot, the object has moved twice as fast. It's moved 2 meters in the same time frame, 2 meters per second. So my next dot for this object is going to go right here. Sorry for the weird noises. My dog is in the room. At 2 meters. So from 0 to 2, and then from 2 to 4. And so you can see that this object has made that trip in a much shorter time. It only took 1, 2, 3, 4, 5 seconds for that object to make the trip, whereas the object down here, it took all 10 seconds. So this is a great, really quick, really easy way to just very visually show and compare the velocities or the speeds for objects. However, we are missing something, aren't we? If you were just given this diagram, you would have no way of knowing where the object started, where it went. The objects could have started here at a position of 1, 2, 3, 4, at a position of 4, and gone to the left and then gone to the right. We have no idea. So maybe it would be helpful to add something to the diagrams that represent the velocity vector. Remember, a vector is a measurement that has a direction with it. And so, since we are talking about velocity, I made clear that the velocities were positive moving to the right. I could add arrows here. Now remember, I could add arrows here to represent a vector. Now remember that a vector always has a measurement and a direction. So if I was going to use arrows to represent these two objects moving, how should I do them differently? What would be the same about the arrows? What would be different? Well, hopefully you realize that this object is moving more slowly, so it's most likely going to get shorter arrows. That is a vector diagram. This other object should get larger arrows, arrows that are about double in size because it has a velocity that is about double. So I've turned this ticker tape diagram or motion map into a vector diagram by adding those vector arrows. Here's an example problem. What if you were looking at this vector diagram and I asked you to calculate or to give me from this the velocity of this object? Well, there are several ways that you can do this. We can just use the mathematical definition of velocity, delta x over t. We can see that this thing has a final position of -5, 6, 7, -8. It It started its journey at an initial position of positive 1. And how long did that take? And this is where you have to be careful. This first dot represents time 0 seconds. Then it starts moving. This dot right here represents time 1. That's where it is at 1 second. Even though there are 4 dots, this is where people always make a mistake, even though there are 4 dots, it only took 3 seconds for this object to complete its journey. This first dot represents the 0 mark, but we do not count. So we count in between. Here's 1 second from here to here. And then from here to here is 2 seconds, and then finally 3 seconds. So it took 3 seconds. So you can see that the velocity is going to be -9/3 or -3 meters per second. Pretty simple. There's an alternate way of doing this as well. You could just look at 2 different dots. This is only true for objects moving at a constant velocity. We haven't gotten to accelerated objects yet. Let's compare these 2 dots. And we know that 1 second has elapsed between them. And we can just find the displacement there. The displacement for every 1 second. Is that not the definition of velocity? So we can say, okay, in this 1 second time frame, it displaced -1, -2, -3. It went backwards 3. So just by doing that, we can also get a velocity of -3 meters per second. Let's consider how we could model accelerated motion using a vector or ticker tape diagram. I've given us some information here. Let's say that we have an object beginning at position 0 at t0. You're always welcome to label the times here to remind yourself this is when we first start our stopwatch, so to speak. This is when 0 seconds have elapsed at t0. And I tell you, this object begins with a velocity, its initial velocity, or its v0. Maybe we could have also called that, to use terminology you're familiar with, its vi, or its initial velocity. It starts out with a velocity of 1 meter per second. So for the first second, its velocity is going to be 1 meter per second. So where's it going to be at t1? It's going to be at 1 meter. So there it is. But this object is accelerating 1 meter per second squared. And this is where we can really start to understand the meaning of acceleration and show it. Hopefully you're aware that this means that each second, I'm going to write this out because it's really important to me that you understand this. Each second, the velocity changes by, this is a positive acceleration. Remember, acceleration and velocity are both vectors. Each second, the velocity changes by 1, positive 1, meter per second. The velocity is already positive. These are in agreement with each other, so this object is speeding up. What do you think that's going to do to our dots down here? Well, if each second the velocity changes by 1 meter per second, here we are this first second, the initial velocity was traveling 1 meter per second. Remember, every single second that passes, we put a dot. I'm going to remind us of that down here. Where in our reference frame is the object going to be? This is t1. Where is it going to be at t2 if 2 seconds have elapsed? Well, if you guys know your acceleration, at t2 it is not going to move 1 more meter right here, but rather now it's going 2 meters per second. That is its new velocity because it's accelerating. Every second that passes, the velocity increases by 1 meter per second. So it moves 1 meters in 1 second. Then it's going to move 2 meters in 1 second. It's getting faster and faster at t2. Where is it going to be at t3? Well, it moved 1 meter, then 2 meters. So now it's going to move 3 meters, 1, 2, 3, and be over here at a position of 6. Every single second, the velocity changes by 1 meter per second. It started out with a velocity of 1 meter per second to get to t1. And then during this interval, it sped up and was moving at 2 meters per second. And then here at this interval, it sped up again, increasing its velocity every second by 1 meter per second. Now it's moving 1, 2, 3 meters in 1 second. Remember, this represents 1 second each dot. Where's it going to be at t4? Now it's going to be advancing 4 meters in a second. 1, 2, 3, 4. This is what these diagrams will look like, and we can change it to a vector diagram by adding arrows. The arrows are going to get longer each time because the velocity is increasing. This is what a vector diagram looks like for accelerated motion. The dots are getting farther and farther apart because every single second the object is covering more ground, the velocity